computer, I guess. So many computers open. Okay. I will not annotate this time, but what this is, okay, we were talking about the char tensor thing. So this just returns a, let's just run all this. So what this cell returns is a tensor that has all of the indexes or the indices of where the characters are in our alphabet. And our alphabet is all characters. It's that string. Does that make sense?
Yes.
Okay. This tensor is not our encoding, and but there is a module that will encode things for us given the indices and the size of the alphabet. Okay, so we're going to skip creating our own GRU cell for now. Here's the RNN.
So we were talking about this part after you left to get your computer working again. And we just were kind of discussing whether we needed to, whether it's enough to just use like embedding, then what's next? After embedding, there's the embedding, ReLU, go through a list of your GRU units, and then use linear on the output. Is that kind of the basis of the forward function that we're going to be using?
That is exactly it.
Because
oh,
awesome.
To take in one index, but that one index needs to be embedded somehow. And then that embedding goes to our series of GRUs. The GRUs output a vector of size, hidden size, but we need to convert hidden size to output size. And so we just pass it through one final linear layer.
Okay. Is it enough to use the embedding as it's listed in the paper, the tutorial paper that we've been using with the view of 1, 1, -1? Is that correct, or?
Say that again.
Oh, okay. Sorry. In the tutorial paper that this lab references, the embedding layer that it has, I'll just post out in the chat what it has at the moment. It just uses this. This one. Is that formatting correct for this chat or for this this code here?
I don't really see why you. Oh, look. Yes, that is correct.
Okay, great. Thank you. I was getting an input error and I was wondering if my embedding was doing it wrong.
Okay. Yeah, I'm getting an input error there too.
Can I ask a quick follow-up question about what you said just like a couple seconds ago? For the forward function, so we want to pass it through the embedding and then through ReLU and then the GRU. But someone said something about an RNN linear. So like after the GRU, do I want to pass it through a linear? And what do I want to pass through a linear? Because I have like my output and my hidden. But I'm kind of confused what you said with like what we're supposed to do with.
So here's the thing. The hidden size is not the same as the output size, and the output of the final GRU will be the hidden size and not the output size. Does that make sense?
Yes. Right now I have my, oh, sorry.
Sorry. Go ahead.
Okay. Right now I have my GRU. It returns an output and a hidden. So you're saying the hidden is the incorrect size?
No. What I am saying is that the output of the GRU
Okay.
is the same size as, okay, well, if you print out your hidden size, I'm guessing it will be 3 by 1 by 200.
Yes.
The output will be 1 by 1 by 200.
Yes.
The output size is not 200. It's 100 or something like that, because that's the size of our alphabet.
Okay.
Um,
Okay.
We'll talk about why the output size and the output of the GRU and the hidden of the GRU are so similarly sized, but the output of the GRU is not the same size as the output of the RNN.
Okay.
And the output of the GRU actually has the same size as hidden size.
Okay.
So I made that very complicated. Any questions?
So I thought the hidden was the output, but like, why are they different, I guess?
Yes, we will talk about that in just a second. But
Okay, thanks.
we're still gonna, we're just gonna talk about the big picture with the RNN.
Sounds good.
Okay, so wait a second. Oh, I just did this thing twice. I don't need this. Okay, so after this, so we're gonna have an embedding. And here it is. Here's the embedding. Now here's what you need to know. The first argument is the size of our alphabet, or the size of our dictionary. The second is the size of the embedding that we want. I don't know how NN.embedding does this internally, but I believe what happens is they do a one-hot encoding of the size of our alphabet, and then does a linear, a matrix multiply to get it to be hidden size. I'm not sure if that's the case, but I think that's what they're doing. They do a one-hot encoding and then transfer that somehow to self.hidden size. Next thing, we're going to have a GRU. And for now, that's going to be NN.GRU. And then, like we were just talking about, we need to go from the hidden size of the GRU to the output size, and we're going to do a linear to do that. Okay. So when we do our forward function, we're just going to pass it through all of these. I'm going to make this f.relu, so it's a functional. Okay, so we embed it. We pass it through the GRU. We do a relu. Sorry, we do a, we make it the right size, and then we do a relu. Any questions about the RNN and what it's doing?
So one other thing we talked about was that making the list of modules, meaning that we make a different GRU for each layer, correct?
Yes.
And then we would just cycle through that list of GRUs?
Yes. So the way that PyTorch's GRU does it is that its GRU has within it a series of GRU cells.
Oh, okay.
And so we're going to kind of follow that paradigm. But really,
Awesome.
okay. You could have done it the other way. But I just think it's really convenient to do it this way.
Yeah.
Okay, so we don't really need to know what the heck this function is doing. Okay, the training function. The important thing to know here, maybe if I draw on my wife's computer, I won't have drawing problems. Let's see. Annotate. Okay, so the important thing to remember is that we've got a vector here of inputs and a vector of targets. So if this were like, if we were inputting the word hello and trying to predict on that, we would get H, E, L, L. And then down here, we would get E, L, L, O. Does that make sense? So given H, predict E, given E, predict L, and so on and so forth. So the inputs and the targets are at the same indice or index. Does that make sense? Oh, you're not seeing the ELLO.
We can see it now.
Okay, there. So you start with the H, go to the E, E to the L, and so on and so forth. It's very common for students to think, oh, I have to index the next one down in the target because that's where it is. That's how people were getting the off by one error. Is when they think, oh, you know, the target string, which is shifted up by one, I should go down one to the L and predict the E from that. Or just down the input string to the E and predict the E from that. Does that make sense? But we don't want to do that. We want to just use the same index for the input and the target. So let's do that. So we're going to start by, oh, it's already done this stuff. Okay. Let's start by indenting it correctly. Okay. So what we're going to do is, okay, now this is just a design decision. We could put the loop that I'm about to do in here by changing this to a sequence of characters instead of just an input character. And that would probably be better for the sake of consistency with the GRU and whatnot. But I'm going to do it here because it's more intuitive here. But we're going to say for C in range, wait, let's see, chunk length. Oh yeah. So for C in the range of the length of the chunk, we're going to predict, and we're going to call our prediction y hat. Y hat is a distribution over the alphabet. And then we're going to store our hidden state. Okay. Okay, I'm passing in input at C. So in the case of hello, that's going to be an H when target at C is an E. Does that make sense?
Uh-huh.
The fact that I am passing in input at C is called teacher forcing.
Okay.
Um,
I thought that was when you passed in the target at C for the next one.
no, teacher forcing is when you put in the target at C minus 1. But the target at C minus 1 is input at C.
Okay, got it.
So now if I were not doing teacher forcing, I would be passing in decoder. I would be passing in a sampled prediction, and I would get that sampled prediction from y hat by picking its top value or something like that. I'd be passing in that prediction and the hidden. Does that make sense?
What do you mean by picking y hat's top value? Is that like taking the argmax?
It would be like taking, yeah, argmax, because argmax returns the index of the thing with the highest value.
Okay, so we wouldn't pass through the sample outputs function that we have below in order to get the prediction character, the predicted character.
The sample function, let's see, does the sample function return an int?
I thought the sample function returned a one hot of the character encoding.
Does it?
It's just right below. It's already coded up for us.
Yeah, let's look at that. Well, it returns whatever the heck torch.multinomial returns. So the real question is how are the PAs using it? No, it returns just a number. It doesn't return a one hot encoding.
Oh yeah, you're right. It returns it as a tensor though still. That's what I was thinking. So
yeah, it does return. Anyway, so, but that's besides the point. If we're not doing teacher forcing, we're just returning the index of the largest output, because that's what the model thought was most likely for the next character. What would happen if we didn't do teacher forcing ever?
I think the model wouldn't learn very well
Why not?
because we would never give it the correct next letter.
Yeah, kind of. So if it makes a mistake on letter Q on the second index, and we're going to have it predict something that's 100 characters long, then every single character after Q was based on the wrong character, right? So it will never, like, it can't really learn that much on the characters after it because it was based on faulty input. So you can't blame those predictions. But on the other hand, the Q is going to be so far back in the gradient, you know, because it's at the second index, that it will learn excruciatingly slow as well. Does that make sense?
Yeah, so it's like the model guesses something. If it's right, that's great. But if not, then we're like, okay, nice try, but let's bring you back to like the correct thing and try again.
Yes, exactly. So if the model, if we correct the model when it makes an incorrect guess, that's called teacher forcing. Now, so you can see why doing no teacher forcing would be a bad thing. In fact, it would be such a bad thing that it just wouldn't really work at all. You would never really learn. But what's the problem with doing teacher forcing 100% of the time?
Would there possibly be a risk of overfitting?
Kind of, not exactly.
Okay.
The problem is that when we evaluate our RNN, we don't have anything to confirm whether an output character was correct or incorrect. And so it needs to learn to rely on its hidden layer. And if it has learned that it will always be corrected when it gets something wrong, and it can rely very heavily on the previous character because it knows for sure that it was correct because the teacher forced it to be correct, then it will rely too heavily on that and not very heavily on the hidden. And so you tend to get results where it predicts based on a very few number of characters before, and it doesn't really have continuity between all of the characters. Does that make sense?
Yeah.
Yeah.
Yeah. So we want the loss function to approximate what's actually going on when we evaluate things. And what's actually going on is that there's zero teacher forcing. So we want to get as close to that as possible, but still learn something and have it not take infinite time. And so that's why it's usually best to do a combination of teacher forcing and not teacher forcing. However, if you just want to get the lab done, just do teacher forcing. It will get you the correct results and they'll be decent and you'll get 100%. But if you want to get a better RNN, definitely try taking the next step and do a combination of teacher forcing and predicting on your own sample. Does that make sense?
Yeah.
Yeah. Yeah.
Okay. So let's move on then. Okay, so now we're going to predict on the, we're going to calculate the loss. Whoops. Okay, loss plus equals our criterion, which is going to be, oh, what's our loss going to be? Cross entropy loss. Okay, I'm going to draw a picture for a second. Let me switch mouses. Okay. Oh, my mouse is not. Okay, so draw. Okay. So if I've got here a vector, and this vector is of probability distributions, cross entropy gives us a target that is a single vector or a single number, like the number 7, which means the index at the thing at index 7 should be the largest, right? And so what it will do is it will compare this distribution to a distribution that is a vector where everything is 0 except for the 7th index is the number 1. and it will try to minimize the distance between these two distributions. Does that make sense? So, but the important thing to know is that the dimension of the target is exactly one smaller than the dimension of the prediction. But cross entropy does require that the target have at least one dimension. So, you know, in the case that this were a vector with lots of different predictions, each one of these predictions would go to a vector, and a series of vectors is called a matrix. So our our prediction vector has to be of 2 dimensions, and our target vector is of 1 dimension. Does that make sense?
Mhm.
Yes. So when you say they differ by 1 dimension, you're saying like one is 2 dimensions and one is 1 dimension.
Exactly.
Okay.
Or if this thing were a matrix like it was in lab 3, I think, then this thing would have to be a 3-dimensional tensor.
Gotcha.
Right?
Yeah.
That's what I mean by they have to differ by 1 dimension.
Okay.
So in our case, oh, oops, I have to transfer the mouse back. So in our case, does anybody know the size of y hat?
1 by 1 by 100?
Exactly, you got it. Which is how many dimensions?
3.
Okay, and does anybody know the number of dimensions for the target at C?
None.
Exactly, there's 0 dimensions for target at C. Target itself is 1 dimension, but when we get an element out of it, it's 0 dimensions. So we're gonna get the single element out and then do unsqueeze. And we're gonna squeeze out the 0th dimension because we don't want to squeeze out the first dimension. Okay, so that will make this 1 dimension, but this is 3 dimensions, and that's a difference of 2. So we're gonna squeeze this one.
Okay. That makes sense.
Does that make sense?
Mm-hmm.
Okay. We do not do lost stop backwards every time. We just do it at the very end because we want the loss of all of the characters together.
And do we also call decoder optimizer dot step outside the loop as well?
Yes.
Okay. Great.
It does not make sense to take a step before you've done lost stop backwards.
Yeah, makes sense. I was just double checking.
Yeah. Okay, and then what we return is the loss divided by the chunk length. Oops, that is not how you spell chunk. And this will give you the average loss for the item. Okay, so does the train loop make sense to everyone?
Yeah.
Okay. Okay, let's talk.
Quick question.
Yeah, go for it.
When you have chunk length, that's the length of the input and the target, right?
Yes.
You have, okay, Cool, thanks.
Which, by the way, is the length of the sequence -1. Because the input's not going to have the last character and the target's not going to have the first character.
So the chunk length and the input size and the target size are all the same, right?
Yes.
Okay, thanks.
Did we run this thing? No, we did not. RNN is not defined. What? Oh, we didn't run this thing. Well, we'll run it, but we don't use the brew. Okay, so that worked. That worked. That worked, I think. Okay, so sampling the outputs. We don't need to change that, but we do need to understand what it's doing. Okay, so a multinomial distribution is like a binomial distribution, except in multiple dimensions. A binomial is just a normal distribution, if I'm not mistaken, and I might be mistaken. So it's going to create a multinomial distribution based on this tensor that we're giving it here. And then it will sample it once. Now what that means is that this is actually being non-deterministic. It's not going to choose the largest element every single time. But it's more likely to choose the largest element or the highest probability density element. Okay, this thing very much confuses me, and I tried to figure out mathematically what was going on here this morning, but I could not figure it out. And I will explain. So when you take an exponential of something, you're making it all positive, and that's great. If you divide by something, then you're bringing it closer to 0, right?
Right. Yeah.
Right.
And things that are closer to 0, when they become exponentiated, the distances between them are smaller because we brought them closer to 0. And the further away from 0, the more extreme they become, right?
Yeah.
Yeah.
So what it seems like to me is that if you were to divide by a number larger than 1, this would make the output be more and more the same, regardless of which one was actually larger. And the closer you got to dividing by 0, the more and more extreme they would become, so that if you were dividing by 0.1, it was sampling the top choice like 99% of the time. So that is what goes through my head mathematically, but I'm very confident that that is actually the exact opposite of what's going on, which makes me feel like mathematically I am not understanding what this line is doing. Because apparently when you divide by 1, you are getting the most conservative sampling of all, instead of the least conservative. Does that make sense?
Yeah. And sample outputs, this is the function you said earlier we would use if we don't want to use forced teaching all the time, right?
No.
Okay.
So the reason why, if you don't want to do forced teaching or teacher
Uh-huh.
forced, then you would want to pick the largest one every single time,
Okay.
because that one gives you the best probability that it gives you the best probability that you're not making a mistake later on down the line. Sampling outputs is simply for the purpose of saying, well, what if I am not confident that this is the most important thing and this is actually the character? Well, in that case, I just want to sample from a distribution instead of literally taking the largest thing.
Okay.
So it gives you the same type of output, but when we're doing not teacher forcing, we want it to be deterministic because we want to hedge our bets. When we're evaluating it, we want it to be non-deterministic so that it can, every time it sees a TH, it isn't going to follow it up with an E and make the word the. Sometimes it'll make the word the, sometimes it'll make the word that, and so on and so forth.
Okay.
Okay, so our evaluation function will look kind of similar to our training function, except that we're going to be feeding back itself. Okay, so the first thing we want to do is we want to create a thought vector, or we want to build up the hidden vector by priming it with the primer string. So we're going to say, oh dear, for C in, well, actually, let's do, I don't like the way the TAs have done this. The TAs from previous semesters, I mean. So I'm going to do it my own way. Okay, for I in, wait, is the primer string a character? Okay, actually, I see what they've done. Never mind, I'll do it their way. Okay, for P in the range of the length of the prime string, we're going to ignore its output, keep its hidden, and pass in the primer input at P.
This is would we be calling the forward function on the decoder here?
Yeah, this is calling the forward function on the decoder that we just studied.
Gotcha. Cool.
Okay, we need to create prime input, and it's going to be equal to the char tensor of the primer string. Oh, oops. Let's take this and put it here.
Okay.
Oh, and we also need to initialize the hidden. What am I missing? Oh, okay. So that's, now we've primed it with the entire primer string, right? Does that make sense how that works?
Yeah.
We just repeatedly pass in the hidden and the prime input, and we don't pass in its own output. But after we're through with the prime string, we got to keep going for 100 more characters.
I have a quick question.
Go for it.
So are we going to use the same hidden layer? No, we're not, because the decoder will output a new hidden layer each time we put in the prime input. Okay.
Yes, it will pass. It will pass back a new hidden layer. The hidden layers will be related, though. We don't know how they'll be related, but there will be some sense of continuity between them. We just don't know how. Anyway, so for I in the range of the prediction length, we're going to, this time we're going to keep our output and our hidden as well. Where is the input? Oh, yes, yes, yes. Sorry. Right here, we're going to say that the input equals whatever the last character of the primer string is. Oh, goodness. Typing is tough, guys.
Tell me about it.
I don't know why I became a programmer. Typing is so hard. Okay, so we're going to essentially say, hey, for the first iteration, the input is going to be the last thing from the primer string. Wait a second. Didn't we already? Oh. Okay, so because the first input is going to be the last thing of the primer string, we're going to go for the length of the primer string -1.
Oh, okay.
Then the first primer string is going to become, the last character in the prime string is going to become the first input of this. But ever
Okay.
after that, the input will be different.
That makes
Okay.
sense.
Yeah.
Um,
That's tricky.
okay, we're going to say that the sampled index equals sample outputs at the output. Okay, what shape is the output?
Output should be
1 by 1 by 200.
Close.
yeah.
That's the size of the GRU's output, but the RNN's output is
1 by 1 by 1?
1 by 1 by 100.
Oh, 100. Okay.
Now, the problem is multinomial is expecting a vector, not a tensor. So we're going to do dot view -1. And that will make it just a length 100 vector instead of
Okay.
a 1 by 1 by 100. And then we're also going to pass in the temperature, which is going to be 0.8 or something like that. So that's going to give us a sampled index of the character that we want from the alphabet. So the character that we want, we'll call it char choice, is going to equal all characters, which remember is our alphabet string, at the given index. Does this make sense?
Yeah, this is making a lot of sense.
Okay, since this is the character that we chose, we can say that the input equals a char tensor of the char choice. And then we can also do prime input plus equals char choice. So the reason I'm doing this last line is because at the end of all of this, we're going to return prime input, and that's going to have the original input plus every character choice after that. So it will be the entire string that it predicted. Does this all make sense?
Yeah, that really
Yeah.
helps clarify that a lot.
Okay, so here's a question. Char tensor is going to have a single number in it because there's only one choice. And sampled index is not a tensor, but it is a single number. Are those numbers the same or different?
The same,
They are the same. Why are they the same?
because that's the index that it predicted for the next character.
So yeah, this is the index that it predicted for the next character. We are literally using it to get the char choice. And if you remember, the definition of char tensor is it returns a tensor with the index. So you could alternatively put here torch.tensor of sampled index, and this would be the exact same thing.
Whoa.
I'm pretty sure. I'm like 95% confident. There's a 5% chance I'm wrong, and so that's why I'm doing it this way, because that's what's in the TA code. But I'm
Cool.
very confident that this is actually the exact same thing. Anyway, okay, so that's our sample and evaluate. So let's run that. It seems to not have a problem. So let's run this for maybe 10 epochs and print every one and plot every 9. The hidden size of 200, 3 layers, and a learning rate of, let's do that. Shall we try it out?
Yeah.
Attribute error. Torch.NN has no attribute grew. Oh. Grew. Oh. Hey, it worked that time.
Quick question for the evaluate function.
Yeah.
Should we be doing it with no gradient at all? Like, because it's an evaluation mode?
Yeah, that will provide a moderate speed up, but it will be functionally the same thing. So if you're running it over and over and over again, you might consider adding with torch.nograd because it will make it run faster. I'm not really concerned about speed of run time. I'm more concerned about speed of debug time right now. And so that's why I'm not doing it.
Okay, just making sure.
So I got an error with the prime input plus equals char choice. It says that it doesn't have a plus equals operator.
What?
Prime input is a tensor, right?
You are correct. What I meant to do is prime string.
Okay. And return prime string too.
Hidden state is not defined.
It worked. Yay.
Interesting. Built-in function or method object is not subscriptable. What? Oh, unsqueeze. Where was that? Yeah, this should be parentheses, not those.
There we go.
Wait, what? Invalid. Oh, I hate it when it does that. Okay.
There we go.
Okay, it's gonna work this time. It's not gonna work this time. Hey, it's working.
It's working. Look at that.
Wait, why is it printing a tensor instead of a string? Oh, I know.
think you need to return the string, right?
Yeah, I. That's why.
There we go.
Yeah, that's not a very good model at first. Hey, at least it's getting rid of some of the crazy characters a little bit.
Look at that. It's getting better.
Anyway, so let's continue on. This all makes sense, right?
Yes, thank you so much. That was really helpful walking
Yes.
through it that way.
Okay, let's see. Were there any questions that were, let's see what questions we had. Okay, so we talked about the evaluation function. We're all happy with the explanation of sampling and evaluation. And we're all happy with our discussion on the training function and the off by one error that's possible in the training function. Is that right?
Yeah, that was helpful.
Okay, so the last thing we need to talk about is making a groove cell. Okay, let's do it. Okay, here's our groove. So each layer does all this stuff. All this stuff would be better in a completely separate class that we will call groove cell, which will also be an RNN module.
Okay.
This is totally just a design decision. You don't have to do it this way, but I think
That's how I would like to do it, is to break it into as many smaller pieces as possible anyway.
Exactly.
Yeah.
Okay, so let's talk about what we're gonna need. Okay, so because groove cell is just one cell, we don't have num layers. So our init function will just take self, the input size, and the output size, which is the hidden size. Does that make sense?
Size and size, yeah. Yeah. That makes sense.
Literally all that's variable. Okay. We'll say self.in. Well, let's just a second. Let me copy paste the code. Okay. Okay, so let's take a look at these equations. Let's define a forward function, which will take as input the self x input and the previous hidden. Okay, there's a reason why I want to call this previous hidden instead of hidden. And the reason why is because we got this GRU cell here. We've got an incoming vector from the previous time step, same cell, previous time step. We also have an incoming vector from the previous cell, the cell stacked above it, or if it's the first cell, the input. We've got a outgoing vector that goes to the next cell in time, and also an outgoing vector that goes to the next cell down. Okay, so we've got all these vectors. This vector is called the hidden vector, and this one is also called the hidden vector, and this one is called the hidden vector, and this one is called the hidden vector. So there's not really much room for confusion, is there?
None at all.
Nope.
So
Clear as pudding.
exactly. So I'm going to call this one the previous hidden, meaning previous in time. I'm going to call this one the input, and I'm going to call this one and this one the hidden. So here's a question for you. Why am I calling these two vectors the same thing if they're different?
Because they're used differently, correct? Afterwards?
They are used differently, but they are actually the exact same vector. We conceptually can think of them like they're different vectors because they are going to different places, but they are actually the exact same vector. So I'm going to call both of them the hidden vector.
Wait, which two are you calling hidden? Because now all four of them are circled.
These two. Does that make sense?
Yeah.
Okay. Yeah.
These two I'm going to call the hidden because they are the same. These two are technically also hidden vectors, but I'm going to call this one previous hidden and this one hidden. These two are not the same. These two are the same. Okay, clear all my drawings. So let's continue on our merry way. Each layer does the following. I'm going to copy this entire comment and put it right here because this is where it deserves to be.
Awesome.
Okay, so what does it mean to do a matrix multiply here plus a bias here. Or better question, more specific.
A linear?
Exactly, that's what I'm looking for, a linear layer. So we're going to create some linear layers. We'll say self dot WIR, but we'll just call it WR, is NN dot linear. Wait, what? That doesn't make sense. Oh, yes, it does make sense. Oh, oops. Wait a second. Oh, I see what they're doing here. Okay. This makes sense. So here's what's what. This plus sign, I believe, is actually a plus sign. So it's saying like take this vector, add this vector to it. But this plus sign, I believe, is a concatenation, not an addition.
That sounds correct from class.
Yeah. So like, that's super frustrating. I'm gonna change this to a dot because in PHP, concatenation is a dot. And I just want to make a distinction between the plus sign and the concatenation, which I think they very poorly made the same sign. This thing too. Okay, with that in mind, we can actually do a bit of math and rearrange this entire equation to be this instead. WIR concatenated with WHR, that whole thing can be multiplied by x at time t concatenated with the hidden state at time t minus 1 plus the bias at IR concatenated with the bias for the hidden state. Does this make sense? How this bit can be thought of as the same thing as this bit?
So to me, it seems like if these weren't matrices, then I would agree. But because they are matrices and vectors, then I'm kind of hesitant because like matrix multiplication isn't commutative.
You are correct. Matrix multiplication is not commutative.
I think it's because it's the concatenation, because you just like stick one on the end of the other. And if you do the same thing in the same order, you stick one vector on the end of the other, and then the bias on the end of the other bias, then you can do it all at the same time.
I actually see what Mikkel is saying, and I think that mathematically these are not the same thing. But what I believe the TAs have done is they have said, because WIR and WHR are just learnable matrices, it actually doesn't matter if we do them separately or together, because either way they're just going to learn. However, this way does allow for the matrices to learn potential interactions between the input and the hidden, instead of just interactions within the hidden and interactions within the input. Does that make sense?
Yeah.
So that is why I believe the TAs have rearranged it to be this way. In any case, that means that this whole thing is one matrix multiply with one vector plus one bias. So they've gone from 2 linear layers down to 1 linear layer. Does that make sense?
Yes, that does.
Yeah.
So we're gonna say self.wr, we've already done that. And this is gonna be for the input R and for the HR, which means that its input size is going to be the size of the input size plus the hidden size, and it's going to go to just the hidden size. Does that make sense?
Yeah.
Okay. They did the same rearranging for the other 3 layers. So instead of typing that all out, I'm just gonna paste all that there. Okay. So these are our 3 matrix multiplies plus biases and whatnot. Okay, so let's start with RT, this one right here. We're gonna do the sigmoid of that linear layer. But remember that linear layer is taking as input the previous hidden and the input concatenated together. So that is going to be, just a second. This whole thing. So we're taking the sigmoid of the linear transformation of the 2 inputs concatenated together along dimension 2.
How do we know it's along dimension 2?
Good question. Let me draw a picture. Well, actually, no. Let me not draw a picture. Okay, so the size of X input and previous input and previous hidden are both 1 by 1 by input size and 1 by 1 by hidden size. So remember, the first one is at index 0, the second one is at index 1, and the input size and the hidden size are both at dimension 2. Sorry, that's what I meant to say. Dimension 0 is 1, dimension 1 is 1, and dimension 2 is input size and hidden size. Does that make sense?
Yeah, so that's the dimension we want to concatenate together.
Exactly, so that it becomes, so that when we concatenate them, this equals 1 by 1 by input size plus hidden size. Does this all make sense?
Yes.
Okay. So that's why we're doing along dimension 2. Because dimension 2 is the 3rd dimension, because 0-based indexing. Okay, we're doing almost the same thing for the ZT and HT. So let me just copy those.
Quick question on that.
Go for it.
Since we're using a linear layer, that initializes the weights and the biases for us, so we don't have to actually do anything with those, correct?
Exactly.
Cool. Thank goodness for linear layers and PyTorch.
Those are
Amen.
Okay, so the H sub t is a little bit different. So let's talk about this one. So they're going to do a torch multiply. Is that is that the Hadamard product? I think that's the Hadamard product, right? Of RT and the previous hidden. And then it's going to concatenate the output of that with X input. So I'm pretty sure this is what we were talking in class about, like RT and the previous hidden are the RT represents what to forget or what to remember. And so RT is being the mask. And when you do the torch dot multiply, it's doing the soft mask. And then, so yeah, that's a Hadamard product. And then we're concatenating that with X, again, along dimension 2, and sending that through the tanh. And that gives us H tilde.
I don't see which equation that's coming from.
I believe that they've called it here NT. So why don't we change that? Let's change that to NT, because that's what it's called right here. That it is this equation. Okay, and then finally the HT. It's the Hadamard product of 1 minus ZT with the previous hidden plus the Hadamard product of ZT with NT. Does this all make sense?
I'm not quite sure why. So I see how NT like is NT because we're taking R and multiplying it by in the commented out code you have like W sub HN times H T minus 1. So that's the previous hidden because it's at H of T minus 1. So then how, I guess I'm like thinking of how was I supposed to know that this first part that says W sub IN times X sub T plus bias, how was I supposed to know that that was, wait, actually, I don't know, could we talk about that part and where that part is in the equation that's not commented out?
Okay, so the WIN plus XT plus the bias concatenated with the, wait, is that concatenated? Okay, well now I'm not sure if that's supposed to be concatenated or plus. But the point is the same still. WIN times TX plus B. Anything that's a matrix times a vector plus a bias is a linear layer. That is specifically this linear layer, self.w. So we're doing self.w of the concatenation of the Hadamard product with the input. So here's the Hadamard product of, wait a second. Oh, the TA's rearranged this equation too. So let's think about this. So they put this bias and this bias together, which means that they also put this matrix multiply and this matrix multiply together. And so what they're doing is they're doing the Hadamard product of this with this. Oh, yeah. So they're doing the Hadamard product of RT and previous hidden, and they're pulling the linear layer out to do it here instead. So they're not doing it exactly the way that a GRU is done, but the wonderful thing about machine learning is that it usually doesn't matter, except when it does.
That's quite
Well,
accurate.
laugh at that.
Yep, that is the wonderful thing.
Anyway, so yeah, they've pulled these two matrices out into one linear layer and these biases out into one linear layer, so that they only have to do one Hadamard product and one concatenation. So
Okay.
Hadamard product, concatenation, and then self.w is the matrix multiply. Okay, so does that all make sense?
Yes.
Yeah, it does.
Okay. So remember with the drawing that I made, I said that the two different vectors that we returned were both called the hidden layer.
Yeah.
Right, yeah.
So we're going to return the hidden layer. We're going to return it twice because they're going to different places, but they are the exact same thing.
Oh, wow. Okay.
So just to make sure, Python isn't going to pass pointers, right? Like it'll make two separate copies that can be handled individually.
No, I'm pretty sure it will pass pointers.
Okay, so
like,
would
you
they be
use it in,
pointing
like-
to the same object?
Yeah, I'm pretty sure they will. But the wonderful thing about Torch is that every time you do anything, it creates a new tensor with the result. So
Cool.
you never do an in-place operation in Torch. And the reason why is because they need to keep everything intact so that when you do the backwards pass, it wouldn't make sense to do automatic differentiation if you could change things in place between backward passes. Does that make sense?
Yeah, that.
So nothing is ever done in place in Torch. So even if you return pointers, it won't matter because when they're used, Torch will create a new thing so that it can keep things clean for the backwards pass. Anyway, okay, so that's one cell.
So sorry, really quick.
Yeah.
I think that HT function looks a little bit off. Because if you look at it in the function definition in the comments, you're doing 1 minus ZT times NT.
Hadamard product with NT.
With NT, yeah, the Hadamard product. But that one's using 1 minus Z Hadamard with the previous hidden.
No,
And
this is
nothing.
the previous hidden. This is NT. Oh. Wait, here, let me, I see what you're saying. Let me, oh wait, what the?
I
Oh,
think they're
Oh, they
switched.
switched it.
you are so right. The TA code is incorrect. Oh my goodness. I need to
3 A's for everyone, right?
push.
For everyone?
You know what's funny about this? The TA's code still produces good results. So, but yes, this is incorrect. I am glad. Maybe sometime on my hours I'll have to push a commit so that next semesters don't have all these errors. Anyway, I'll probably push a commit to undo pulling these linear layers out as well. I don't know if it works better or less good, but I do think that it would be better to have it be consistent with what the equations actually are. Anyway, that doesn't matter. We're going to return these two linear layers. Let's talk about the overall GRU now. Yeah, or do we have other questions?
I'm good to go on.
Yeah.
Okay. Okay. So the GRU is taking input size, hidden size, num layers, all that good stuff. So let's just copy this and paste it here. Cool. First thing is, because we have an unknown number of layers, we're going to need a list of GRU cells. The problem is rnn.module, when it calls dot parameters, it will only go through each of the children to check if each of the children are nn.modules to call their dot parameters. It will not, so if we have like self.a equals an array of layers, like L1, L2, L3, it will not go inside this array and check if each of these are modules. So because of that, the parameters would not end up being registered with the optimizer. They would not be part of the backwards pass and all this sort of stuff that would be very, very bad. So we cannot use an array. Luckily, Torch created this nifty thing called nn.module list, which takes, wouldn't you know it, an array. So let's call this module list GRU cells. Then for num layers, we're going to put a GRU cell inside of the module list. So for every layer in the range of self.num layers, we're going to define what the input size is. The input size is going to be the input size for the first thing if the layer equals 0. Otherwise, it's going to be the hidden size. So self.GRUCells.append a GRU cell of these dimensions. Does that make sense? Yeah? The most important thing to remember is just that, because this might come up later in your careers, you cannot use an array, you must use a module list. Otherwise, they will not be registered as modules in dot parameters, in dot backwards, and all these other sorts of things.
Noted.
Okay, so then the forward function okay, so the forward function, let's draw a picture for a second. Let me switch the mouse so I can draw a picture. Okay. If we've got a module here, it takes an input, gives an output hidden. It takes an input from above as well as from the previous time step. And it gives its hiddens on down. This vector and this vector are the same. And we go on and on. Okay, so here we've got 3. So our GRU cell returns 2 things, this vector and this vector. And they are the exact same, but our GRU overall is going to return the hiddens and the outputs. And this thing, all 3 of these concatenated together are the hidden. That is why they are of size 3 by 1 by 200, which is the hidden size. This guy is just 1 by 1 by 200. So this guy right here is this guy. Does that make sense?
That helps a ton to see it like that.
Yeah.
So when we do the forwards, we're just going to concatenate all of those 3 hiddens together along that specific, along dimension 0. Okay, so let's just do that. Where's my mouse? Oh, my mouse is on the other computer. Okay. I'm just going to copy this entire thing. Okay, so outputs and hiddens equals the first GRU cell. And then for the rest of them, from 1 till the number of layers, we're going to take the outputs of the previous layer and the hiddens of the previous layer and feed them in right here. Oh, sorry, no. So this hidden is the previous hidden, which is, you know, the 3 by 1 by 200 of the previous iteration. And so that's why we're slicing into it right here from the layer we want to the layer we want plus 1. And so that will return a 1 by 200. So this hidden layer is not the hidden layer from the previous iteration, it's the hidden layer. Wait, let me think about this. Oh, yeah. This is the hidden layer that we want to pass on to the next iteration. And so we're going to concatenate it along dimension 0 with the hiddens. Does this all make sense?
Can you explain why you slice the first, like the hidden that's put in the forward at the very beginning, the 0 to 1?
Excellent question. So slicing is inclusive on the left and exclusive on the right. So this is essentially saying, get the thing at index 0. The only difference is that it returns it without changing the dimensions of the tensor. If we just got the thing at index 0, it would be a 1 by 200 tensor. But since we're slicing, it's a 1 by 1 by 200 tensor.
Okay.
Oh, that makes sense.
And the only reason we're doing that is to keep the dimensions consistent between all of the things.
We just need the 0th layer. I mean the 0th part of the hidden.
Excellent question. Let me draw a picture.
Pictures are nice.
Yes, pictures are very nice. Okay, so we got 3 cells here. That was a terrible cell, but oh well. So we've got 3 vectors coming into them. And all 3 of these vectors concatenated together are what we are calling hidden right here. These same three vectors coming out, all three of them concatenated together are what we are calling hiddens right here. They're totally not the same thing. Hidden and hiddens, totally different. Could never confuse them. This GRU cell does not need to know about this guy or this guy. He only cares about the one that's coming into him. So we're going to slice him out of all of them. Does that answer your question?
Yeah, but why is that not a part of the for loop? Like, are we ever going to slice the second
Oh, yes, yes.
one underneath it?
So that's a good question, and we are. So, so right here, we're just doing the first one. Oops, I accidentally crossed that out. But right here, we are doing the exact same thing for the next layer and for the layers after that. So we've just pulled the first layer out of the for loop and then done all the layers after that in the for loop.
Okay,
And
is
that's
there
just
a
so we
reason?
could get the hiddens thing initialized, right?
Yeah, so that we could concatenate to it afterwards.
Got it.
Okay, any other questions about how this forward is working?
So outputs, that's the output going vertically in the diagram, right?
Outputs is the vector that's coming here. Oh yeah. So yeah, outputs is going from here to here and from here to here.
Yeah, okay. But it's only one of them in the end, right? It's just the last one?
Yeah, in the last iteration, it's just the one coming here. And remember, this guy and this guy are the same, but conceptually, we're thinking about them as though they were different because they're going to different places.
Got it.
Okay. I'm not sure who talked about having the issue with random output, but I was able to fix it by making changes to my RNN that he described. Well, that's good, Talia. Okay, so I think that this all makes sense. So let's switch the mouse back and move on. Okay, I think that's pretty much everything, right? Let's just change this from nn.gru to simply gru. And that should work. Okay, while this is running, do we have any questions?
For the final IPython notebook that you want us to turn in, should it be using our GRU model, like the outputs that are shown on that?
Yes, if you want points for doing it.
Okay, sounds great.
So we'll probably, like, if you create your GRU but don't use it, you'll probably get like, well, let's look at the grading rubric. Implement your own GRU. You'll probably get most of those 20%, but not all of them, because we want to see that your GRU actually works.
Cool, makes sense.
So if you make it but don't use it, I don't know. I'll have to talk to the TAs about exactly how much we take off for that. But anyway. Do you have any other questions?
Any suggestions on like how long to train or like other things like that?
Yeah, train until your lost plateaus.
Cool. Sounds good.
Most people are doing it, you know, around 5,000 epics. I think printing every 10, if you're doing 5,000 is too much. I would print every 100 and plot every like 1,000. Anyway, any other questions?
Joseph, do you know really easily how to save a module onto your computer so that you can train it and load it back in later and keep training it so that if it times out or something, you can keep going?
Somebody answered that question in Slack. I don't remember how to do it off of the top of my head, but I could Google it.
Okay, I'll go look at it on Slack. So
yeah. Okay, well, if that's all the questions, then I'm pretty far over time, so I think I'll stop the share and post this.
Thank you
Thank you so much.
Thank you so much.
Thank you.
Thank you.
Thank
You're
you.
It's amazing.
welcome.